If you've used ChatGPT in the past few months, you would have noticed that they added a feature called memories. Now, this allows ChatGPT to give you, the user, personalized responses, not only on a single conversation, but infinitely across all of your future interactions. Today, we're going to be implementing this type of long-term memory into an AI voice agent. And we're going to be using a platform called Mem0. Now, this is a type of memory solution, and it's not only faster, but also more accurate than OpenAI's implementation. Okay, let me give you a real world example of how, this type of long-term memory could be actually useful. Say we are building an AI voice agent for a restaurant. Now, this is a very, very common use case and one that I've built before. And the user tells us or tells the AI voice agent that they are a vegetarian. This piece of information would be stored into the long-term memory of the agent using Mem0. And let's say that, after that interaction, a few months go by and the user calls again and asks for some recommendations. The AI would retrieve that previous memory and use it in its response. So, for example, there, it would only recommend things on the menu from that restaurant that are vegetarian. This gives the user an experience they probably wouldn't even be able to get from a human, unless obviously the receptionist at the restaurant was really, really good with remembering a lot of different facts about a lot of different people. But obviously, for an automated system, it is much, much easier. So yeah, that's what we're going to build, a long-term memory system for an AI voice agent. All the resources from this video, all the code, everything like that will be down in the description below for you to download completely for free. Okay, so this is how a usual system looks like. We've spoken about this on my channel a million times. If you are familiar with voice agents, you will know exactly what this is. Now, here is how it's going to look like for this long-term voice agent and how the system and architecture of the voice agent looks differently based on adding this kind of Mem0 ability. So what we have is the speech to text. What it's going to do is the transcribed speech is going to go into two relevant areas for Mem0. The first one will be Mem0 add, which basically will add every single message that has been transcribed. So all of that kind of short-term memory in the sense that we have the entire conversation, all of that will be added into Mem0 at every turn. And that will be all messages but the system. So every time there's a new message added, we take that entire previous messages or the entire conversation history, and we will send that to Mem0 add. As you can see, it is not connected with anything else. So it is a background task that is happening in the background. Next, we have Mem0 search. Now, what we do here is we take the last two user and the last two assistant messages, and we use that as a query to search Mem0's prior or stored memories. So here we're adding new memories, and Mem0 handles the adding itself. So all we need to do is, send these messages to Mem0, and it itself retrieves and basically decides, do we need to add any new memories, which makes it very, very easy for us. And then we get that query and we use Mem0 search to try to find some relevant memories based on the query. Then all the relevant memories, sometimes there's none, sometimes there are 3, sometimes there are 5, will be added into the LLM's system prompt so that it has those relevant memories as context to respond. And then obviously we go to the text to speech. So let's start the code and I will give you a demo first thing so that you can see this long-term memory in action. As you can see here, my server has started up. I'm going to grab this ngrok URL right here, and we're going to paste it into Vapi and save this assistant. So now what I'm going to do is I'm going to give this number a call because I have it connected to a phone number. Let's give it a ring.
Hiya. Hi, how can I help? I just wanted to let you know that I'm vegetarian.
Thanks for letting me know. I'll keep that in mind for any food-related suggestions.
Cool. And I also wanted to let you know that I have a dog called Luna.
Got it. Luna sounds lovely. I'll remember for any pet-related chats.
Cool. I'll talk to you soon then.
Take care, mate. Say hi to Luna for me.
Cool. So I just gave it a few pieces of memory. Obviously, in an actual AI voice agent or in a production thing, there would be a reason to the memories. This was kind of just to showcase the ability. Now, I would be able to call this number. So I called a specific number, which was, the number that my AI voice agent was running under. I could call this number in 3 years and these memories would still be saved in mem0. So if we were to reload, the reason why I was showing you no memories is because now you can see 1 minute ago, user owns a dog named Luna and user is vegetarian. Both these things were kind of decided by mem0 to be relevant memories that should be stored. So it also even labeled categories, so miscellaneous, and this one was user preferences and food, because obviously user is a vegetarian. Now, if I were to, like I said, call in a year, this system would still work. So that's why I call it long-term memory. I can just call it again now and show you it working, however.
Hello.
Hi, do you know what my dog's name is?
Yes, your dog's name is Luna.
Okay, cool. And do you know my dietary preferences, maybe?
Yes, you're vegetarian.
Cool. I'm not even going to talk more. You can see it was able to retrieve those relevant memories. And so essentially, when I said, do you know what my dog's name is? That transcribed text was used as a query to send to mem0 search. And based on that, it responded with the memories. So if I were to go into requests right here, we could actually see the requests that are happening live. So less than a minute ago, one of the add event types was done. So that would have been this mem0 add. And we also had a search, and both these are roughly happening at the same time. So that's why you can see the timing is the same. So the mem0 add takes 4.27 seconds. So the latency does add a little bit of time, but luckily it is background and therefore it doesn't really matter. However, the search does matter because we do need to get the search back before we get the LLM response back. So it does have a latency of 68.82 milliseconds, roughly 68, 63. It just depends, but around sub 100 milliseconds, which is pretty good. And it doesn't add too much latency, depending also on where you are locally. I'm assuming mem0 is hosted in the US, and therefore if you're like me in the UK, you add some latency by querying and sending network pings to the US, because it's going to take around a 100 milliseconds anyway to come back. So usually for me, it is around 200 milliseconds latency. But like I said, if you were in the US, it would be much shorter. So if we were to look at actually, the search maybe. So we go into the search and we can look at the query, and the query says, assistant, hello, question mark, user, hi, do you know what my dog's name is? Assistant, yes, your dog's name is Luna. Okay, cool. And do you know my dietary preferences? Maybe. So this is the query. And in the retrieve memories, we get 2 memories. We get user owns a dog named Luna and user is a vegetarian. So both those memories would have been inputted into the LLM system prompt through the code. I will show you that in a second. And therefore it responded with, yes, I know you are a vegetarian. It didn't use the my dog's name is Luna because that question was already asked before. And the AI knows that my previous question was, do you know my dietary preferences? So we can also look at when and where those memories were added. So if we scroll down to the first conversation, here we can see +2 add, which means 2 memories were added. So if we look at this, messages, hello, hi, how can I help you? I just want to let you know that I am vegetarian. And in the user memory action, we add a user is a vegetarian and the user owns a dog named Luna, which is weird that it added user owns a dog named Luna because it doesn't seem like I said that in that message. Let me check that again. Yeah, I guess it decided to something about the printing will be wrong there, because obviously mem0 wouldn't add that randomly. So yeah, as you can see there, that kind of adds the memories, and so that kind of helps to explain the chart. So now let me go into the code and show you exactly what we're doing to basically achieve that graph and achieve that long-term memory through mem0. So first of all, we're going to do our imports in Python. Again, I always code in Python just because it's the easiest, like to get things up and running. And I mean, yes, there are quicker softwares, but I don't think shaving, maybe 3 milliseconds is that important in voice AI, since there's much easier and more important ways to shave latency in other areas. So what we do is we load or sorry, not load, but initialize the async memory client, which is from M0, as you can see here in this import. And we also initialize the OpenAI client, but we're initializing with Cerebrus using the Cerebrus base URL and my Cerebrus API key, because we are using a Cerebrus LLM for lower latency. We set up logging, we set up the app, we set up cause middleware, and then we can start with the actual functions and all the logic of the code. As you can see, it's not that long of a code, so it'll be very simple for me to explain. So we have a search memory function that I have defined right here, and this does exactly what you would think it does. It is this part right here. So what we do is we input the messages, so everything from the speech to text, the entire list that we get back from VAPI, and we get the user ID. So the user ID, I'll show you how we do that later, but we get the user ID as well. So here what we do is we build a query from the last two user and the last two assistant messages, like I mentioned right here. So what we do for that is pretty simple. We get a collected list, which basically an account, to make sure that we're counting up to the point to where we have two of each. And what we do is for message in reversed messages, essentially meaning we go through the messages list, but we do it through the reverse so that we're actually getting the most recent messages, because the most recent message is at the bottom, not at the top. The top is the system, then it's the first message, then it's the second message. And so the last message is the message that was the most recent. So that's why we do a reverse. Then what we do is we get the role to check, the role. And if role is user or assistant and the counts, so right here, is less than 2, then we basically get the content. So that would be get whatever the user or the assistant said. And then if there is content, so if it's true, because sometimes maybe there's an error and there is no content for some reason, then we append that content and the role into collected. So this collected will now have the role and the content. And then we add 1 to the count of the role. So if we just did the user message, we add 1 to the user, so that we now know we've gotten one of the user messages. And then we just do that until we have 2 of the user and 2 of the assistant. So greater than or equal to 2. So break, and then we return those collected messages. So if not collected, basically meaning if there's an error, we just return those messages. This is kind of just like some error handling. Then what we do is we reverse it, because technically we grabbed the most recent message. So we grab the most recent message, then we grab the second most recent message, then we grab the third most recent, then we grab the fourth most recent. So in the query, it actually looks like the bottom one is the most recent. So we want to reverse it so that the top ones are actually the bottom ones and are the most recent. Sounds a bit confusing, but it just makes sense. So it's the chronological order. So then in the query, we basically just take this collected, as you can see here, so for role text in collected, and we basically just turn it into a nice looking query, which we then send to mem0 using await m.search. So m is obviously the memory client, m.search with the query equal query, user ID equals the user ID that we get from the top of the function, and then the threshold being 0.2. This basically just means how confident are we with the memories. So as you saw with one of the memories I showed you, let's go and search here. In the retrieve memories, you can see the threshold or the confidence score is 0.64 and 0.48. So if we were to have a confidence score for a memory that was maybe 0.19, that memory would not be added or not be retrieved because our threshold is 0.2. So we fetch those memories, and then what we do is we just turn those memories into some readable text. So we get the memory, we get the content, and then we get the text. And we basically just append those together and turn it into this little context block, which is just text saying relevant memories only used if necessary and useful. And then the lines, which is basically just all the lines of the memories, and that will be sent or used in the system prompt. So then, as you can see, the context block is then used right here. So if system content, we grab the system content, and we add the context block right next to it. And now we have our system prompt plus the context block right at the end of the message. So this is just basically making sure that there is only a single system message, which there will be. And if it does exist, append the context block to the system message. Here, it basically just checks to make sure there's no duplicates, and then we return this kind of deduped, meaning there are no duplicates. And that means, and deduped is the entire messages with the system prompt slightly appended with memories. So that is what we are returning. Then we have a background add memory. This does exactly what you would think. This does the mem0 add. And here what we do is we add the user ID and the messages just like we did for the search memory function, exactly the same. And what we do here is we collect all the non-system messages. Like I said, we have all the messages but the system, and then we simply add it to mem0. So as you can see here, await m, again, the mem0 client dot add payload, meaning, the messages right here, which were created through here, and the user ID, which again, we pass at the top of the function. And then there's a quick little exception, which is just error handling. So app.post/chat/completions. This is the API or the fast API router for VAPI. As you can see here, VAPI will use HTTPS and grok/chat/completions because that is how they expect it. So that's why we need to make it an app.post and for VAPI's formatting. So what we do here is we get the request. So as you can see here, and we do payload equals await request.json. This is basically just getting all the requests. Then we print it. So you don't necessarily need to print it. I just printed it so that I could know the format of the VAPI payload and use it for the code. So what we do is we get the messages, as that is, part of the function for both of these. Obviously, we need to pass the messages in for both those functions. And we also start the time. This is for time to first token because I wanted to know what the latency of mem0 is. We also get the phone number. So this is pretty simple. We do equals payload.get customer or .get number or payload.get call or get customer or get number. There's a ton of areas that the VAPI or the customer's phone number is in the payload. So there's multiple ways we can get the number. Then what we do is we create the user ID. So we could just use the phone number as the user ID, but potentially there could be issues there. And so instead, what I do is I turn the phone number into a UUID. So if you don't know what a UUID, it is just like the numbers that usually like an API key is a UUID. This is what a UUID is. So we're turning that phone number into a UUID by using UUID5. So if that makes sense, it's just going to have a user ID. Actually, we can go into mem0 and this is the user ID that was created from my phone number. Hopefully you can't retrace my phone number through that. But yeah, that's the user ID that was created. So that user ID is going to be the same every time with the same phone number, which is good because we need a deterministic user ID so that we know it is the same person based on the phone number. Then what we do is we create that non-blocking memory add, which basically sends a create task asyncio for the background add memory function that we created and defined over here. And we pass in the user ID, which we created over here, and the messages that we got from the payload. Then what we do is we get the messages with the memories. So the kind of updated messages, which has the system prompt that has the memories within it. And we do that by doing await search memory. And again, we input the messages and the user ID. Now, once we've returned the messages with memories, we are ready to go and get a response from the LLM. And so what we do is we do stream equals O, which is the OpenAI client, or actually technically the Cerebrus client, .chat.completions.create, and we input the messages with memories. And then model equals payload.get model because VAPI sends the model name. It is anything that we define right here. So we get that. We have a fallback of the Qwen3 model. Stream equals payload.get. So we get what VAPI decides to do. It's always going to stream. but we have a fallback as true. Max completion underscore tokens equals payload.get max tokens 250 is the fallback, and etc for temperature and top P. So this is going to get back a stream, and we're going to be passing that stream through this function that we have called generate. So generate essentially does very little, but what it does is it checks to see if the first chunk equals true, and if it is true, it will basically turn that first chunk now into false, so kind of like a lever, and then basically print and log the time to first token. So I cleared the logs, but the time to first token was around 1.1 seconds, which is a little bit on the higher end, but I'm sure there's ways to optimize it too. And I think a big issue of that was Cerebras, because if Cerebras's time to first token was like 200 milliseconds and mem0 was 200, then it really should be 400 milliseconds. So I think there's a mixture of both reasons as to why the time to first token was so high. So then what we do is we take the chunk, so the chunk in the stream. So as you can see, 4 chunk in stream. So the stream is coming from the Cerebras stream, and we model dump JSON it. And basically this is the format and response format that VAPI expects, sorry. So then we yield data colon JSON data, which is, you know, this right here, with 2 new lines, and that gives us what VAPI expects, sorry. And then because we're actually returning a stream, what we need to do is we need to do return streaming response and generate. So this is the function that we defined there, with media type equals text / event stream, and now VAPI will know that we are streaming back and to them, and it will handle it correctly. Now we have some error handling. We have a health router, basically just to check, or health route, I guess. I don't know what it's called technically. Just to check basically if the fast API server is working, if the ngrok URL is working. And then we have this little last bit, which is if name equals main, import uvicon. We set up the ngrok terminal and we copy that public URL. So as you saw earlier, I copied that public URL and added it into VAPI. And then from there, we are good to go. And we use uvicon.run to actually run the app. And that is it. So that is how you add long-term memory. All the code will be down in the description below. Like I said, for free for you to just do yourself. The only really things you need to change in this code is your API key. You can make it OpenAI, you can make it Grok, you can make it any OpenAI compatible LLM provider. So essentially all of them, because they all built off of OpenAI's Python SDK. And you're going to need to set up ngrok, which is very, very simple. And finally, you need to do nothing else except for adding the custom LLM URL into VAPI for the assistant. And obviously, oh yeah, and sorry, and in your .environment file, you need to put in the mem0 API key. And I think that is it. So thank you for watching, and hopefully that was a useful tutorial for anyone who's looking to build and implement long-term memory in their AI voice agent system. And I will hopefully see you in the next video.